Section 7.8 is about these things called improper integrals. Up until now, anytime we've done a definite integral, we've needed two things to be true. We've needed a finite interval, that is, the integral goes from some number a to some number b, and we've needed the function to be continuous in between a and b. So continuous function on a finite definite interval. But now we're going to ask to do integrals where one of those conditions isn't true. So that is, maybe sometimes the interval will be infinite. We'll go from a number up to infinity, or from negative infinity to a number, or even the entire real line from negative infinity to positive infinity. Or, that's called an improper integral of type 1. Or we might want to do the integral of a function that is not continuous, either at a or b or in between a and b. We still want to be able to do that integral, and that's called an improper integral of type 2. So improper integrals are integrals where either the bounds of integration are infinite, or somewhere in the area you're integrating in, the function isn't continuous. Okay. In this video, we're going to talk about the first type of improper integrals, where you go from a number to infinity, or negative infinity to a number, or negative infinity to positive infinity. So what if you want to start at a number a and integrate all the way to x equals infinity, which isn't really a number? What does that mean? Well, the picture looks like this. We have a function, we have a number a, and remember the definite integral represents the area, the signed area, between the graph of the function and the x-axis. So it starts at a, but it just kind of keeps going. We want that area. To find that area, what we'll do is find the area up to a value, t, but then keep moving that value t further and further and further to the right, so we'll take a limit. So we want the area from a up to t, and then we'll take the limit as that t value approaches infinity. So this is the definition of the integral from a to infinity. The definition of that integral is you have to take a limit of the integral from a to t and let t approach infinity. Okay. If that limit either doesn't exist, or is infinite, or is negative infinity, we say that integral diverges. It doesn't have a value. However, sometimes that limit will equal a number. And if it does, we say the integral converges, the improper integral converges, and its value is whatever number we got. Okay, so here's an example. The integral from 2 to infinity of the function 1 over x cubed. And we want to know either what that value is, or we want to show that the integral diverges. So here's a picture. The function 1 over x cubed looks roughly like this. This is a very rough drawing, but we start at x equals 2, and we want all the area to the right of that. And by definition, if I want the integral from 2 to infinity, what I need to do is take the integral from 2 to t, and then the limit as t approaches infinity. X to the negative 3 is easy to integrate. It's x to the negative 2 over negative 2, and I'm plugging in t and 2 and subtracting. So if you plug in t, you get negative 1 over 2t squared. If you plug in 2, you get negative 1 over 2 times 2 squared. And we're subtracting those. Simplify a bit. 1/8 minus 1 over 2t squared. And I want the limit as t approaches infinity. Well, as t approaches infinity, 1 over 2t squared is 1 over really, really giant numbers, so that goes to 0. So I have 1/8 minus 0, which is just 1/8. Since the result is a number, the result of doing that limit is a number, that means the integral converges, and its value is 1/8. Here's another example. Again, I want the integral from 2 to infinity, but this time instead of 1 over x cubed, I'm just going to integrate 1 over x. The picture is roughly the same. The graph of 1 over x and the graph of 1 over x cubed look very similar. And we do the same procedure. The integral from 2 to infinity, I have to do the limit as t approaches infinity of the integral from 2 to t. But this time the integral of 1 over x isn't x to a power, it's the natural log of the absolute value of x. All the x values here are positive, so I don't really need the x to be in absolute values because it's only 2 and bigger numbers for the x values. So I need the natural log of t minus the natural log of 2, and then I take the limit as t goes to infinity. Well, as t goes to infinity, the natural log of infinity is also infinity. So what I end up with is infinity minus the natural log of 2, which is infinity minus some small number. That's still infinity. Since the limit is infinite, that means that the improper integral diverges. So it doesn't equal a number. There's no number for the answer. That's an infinite area there. That's very strange. The picture looks similar, but in the previous example, that entire infinitely long area, very long and skinny, was just 1/8 of a square unit. But here, it's infinitely big. The area is infinite. The integral diverges. Okay, the other kinds of type 1 improper integrals would be starting at negative infinity and stopping at some number. Right? And that's just sort of the opposite of what we just did. And you treat it the same way. You start at some number t and go up to b, and then take the limit as t goes to negative infinity. So we're sort of moving that left-hand endpoint farther and farther left to get all the area. And then if you want to have the integral that starts at negative infinity and goes to positive infinity, so you want the entire area from all the way on the left to all the way on the right, what you do is you just, anywhere in between, pick a point to break it apart. So now we're going to break that area into two pieces, to the left of a and to the right of a. Right, so we have the integral from negative infinity to a, that's the left-hand part, and the integral from a to infinity. Well, each of those we already know what to do, right? The negative infinity to a, the description is the top half of this slide, and the a to positive infinity we did previously. So each of those two separate integrals is a limit. Each of those is an improper integral, and we have to do the limit. And if they both converge, if both limits give you, if both limits each separately give you a number, then you add those two numbers together, and that's the value of this entire integral. If either one of those separate integrals diverges, or if they both diverge, then the whole integral diverges. I want to point out that where we choose to break it at a, I've marked there, it doesn't matter. You can let a equal 0, you can let a equal 1,000,000, anywhere that's convenient. It should not affect the final answer. There's a second video on 7.8, and it will describe how to do the other kind of improper integrals, the ones where you're going between two numbers, not infinity or negative infinity, but in between those two numbers something bad happens to your function. So that's in the second video on section 7.8.